how to calculate the maximum power transfer through the load resistor. Now to find this one out, first we have to know the power equation. Power is given by P is equal to V times I. And if you apply Ohm's law, you can also rearrange this one and make it as I square R. Or you can also write it as P square divided by R. Okay. So here I is equal to V Thevenin. If I apply Ohm's law, that is I is equal to V divided by R. In this case, this is V Thevenin divided by these two resistors are connected in series, so they're going to add up, and that's going to be in the denominator R load plus R Thevenin. And if I write the power equation for this is going to be power is equal to I square R. And instead of I, if I replace this one, V Thevenin over RL plus R Thevenin, this is going to become V Thevenin divided by RL plus R Thevenin square RL. And here you can you see that we have a arrow sign at the L load resistor. It means this resistor is the only one that's adjustable. This V Thevenin and R Thevenin act like a constant, because here we are going to find maximum power transfer. To find out the maximum power transfer, what we have to do is we have to take the derivative and equate this one to 0. So when we take the derivative, we can only take in terms of load resistor, because that's the only value we can change. These two are gonna act like constant. Okay, now let's go ahead and see that. Here I can rearrange this power equation by taking the V Thevenin out. V is equivalent to V Thevenin square times R load divided by R load plus R Thevenin square. Okay, so you can see that I just rewrite this equation in a different way. I just took out this V Thevenin and put it outside, and RL inside, and then RL plus R Thevenin square in the denominator. Okay, now we are going to do the derivative. If you study calculus, differential calculus, you know that when you take derivative, you can find the maximum or minimum value. So here, this is the maximum value we are going to find. So you just take the derivative and make it equal to 0. So here we have to take the derivative in terms of RL, because that's the only value that changes. dP divided by dRL, and V Thevenin and the R Thevenin is going to act like a constant when we do that. It's equal to 0. Therefore, V Thevenin square, the derivative is going to be V Thevenin square, and then RL plus R Thevenin whole square minus times 1 minus RL 2 times RL plus R Thevenin 0 plus 1 divided by RL plus R Thevenin power 4. Okay, now let's simplify this one furthermore. If we do that, this is going to become V Thevenin square divided by RL plus R Thevenin power 4 in the denominator, and then that one multiplied by RL plus R Thevenin times RL plus R Thevenin plus, not plus, actually minus 2RL. Minus 2RL. If you notice here, we can cancel this RL plus R Thevenin, 1 power with this one. This is also R Thevenin, RL plus R Thevenin. Let me put another bracket so it will be clear. Okay, here I'm going to cancel this one. Let me use a different color. This is going to be 3 power 3, and I cancel this whole thing. So this is the only one left, and then V Thevenin square divided by RL plus R Thevenin cube. Let's bring it down. Oh, do I have space? Let me copy this one in the next page. I'll create another page. Okay, So we cancel that one. After we cancel, this is what we are going to get. 0 is equal to VThevenin square divided by RL plus RThevenin. We cancel one of the power, so this cube right now, and then this one multiplied by RL plus RThevenin plus actually minus 2RL minus 2RL. Okay, and if you simplify this one furthermore, this is going to become VThevenin square times RThevenin. Here we have an RL minus 2RL, that's going to be RThevenin minus RL, and in the denominator we are going to have RL plus RThevenin cube. Okay, the whole thing is equal to 0, and if you simplify and solve for this, you are going to get RThevenin is equal to RL. Okay, you can prove that one by simplifying this one furthermore. Now once you have this, what we can do, we can, now we know that RThevenin is equal to RL, then look at the equation we had before. Let's bring this equation back. Okay, so when so we are trying to find maximum power transfer. So when the maximum power transfer, RThevenin is equal to RL, and if I bring this equation here, let me copy this one and paste it here and replace everything. I'm going to copy this and paste it somewhere here or new page. Okay, paste it here. Let's bring it here. And in maximum power transfer, RThevenin is equal to RL. So what we can do here is we can replace all the RThevenin with RL. So this is going to become VThevenin square RL divided by RL plus, instead of RThevenin I can put RL here square, and that's gonna become 2RL square, VThevenin square divided by 2RL square, or you can write it as 2 square RL square, that's going to be 4RL square, and then we have RL in the numerator. One of the power can be cancelled, and that's going to make this one VThevenin square divided by 4RL, or you can also write it as you can also write this one as power is equal to VThevenin square divided by 4 RThevenin, because RL is equal to RThevenin, so you can write like this one as well. And that's the final derivation for power maximum power transfer. This is the equation we have to use. I hope you guys find this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.